Our last speaker today is Dr. Charan Ranganath, professor of psychology and a core faculty member at the Center for Neuroscience. Dr. Ranganath got his Ph.D. at Northwestern University and did his postdoctoral training at UC Berkeley. He's received numerous awards, including a Guggenheim Fellowship, Leverhulme Trust Visiting Professorship at the University of Cambridge, the Laird Surmark Award from the Memory Disorders Research Society. He was a UC Davis Chancellor's Fellow and received a National Security Science and Engineering Faculty Fellowship. Professor Ranganath is a New York Times bestselling author and one of the world's leading memory researchers. His groundbreaking research explores how memory shapes who we are and how we think. So please join me in welcoming Professor Charan Ranganath.
Thank you. It's exciting to be here, and thanks for everyone to come and spend your Saturday learning about the brain. I wanted to start, I feel slightly guilty altering the template, but I always want to start off by showing the people who really do the work in our lab. And actually, this is the best picture I have in my lab taken by our own Kimberly. And it just so happens I have one extra lab member who's Marilou Henner, who's actually an actress from the TV show Taxi. She actually has highly superior autobiographical memory, which is a phenomenon where people can remember all sorts of amazing details from their lives. You can give any date to her, and she can remember the day of the week, the weather that day, what she ate for lunch. It's an absolutely incredible condition, and she spoke to my class, she spoke to my lab about it, and I texted her, and she said it's okay to use this picture. So she's kind of an honorary lab member now. That was a very memorable event, and I guess the reason I wanted to show this is that I've been trying to spend a lot of my time now investing in memories in my life, and I think this is an important thing to do because I think we don't always remember everything, right? I opened up my book, Why We Remember, with this quote, which is, my ability to remember lyrics of songs from the 80s exceeds my ability to remember why I walked into the kitchen. And I think for many of us, especially for those of us over the age of 30 or 40 or 50, certainly you find yourself walking into the kitchen and forgetting why you ended up there. And I've certainly consumed many empty calories because of this problem. So, in case you can't tell. And so I'll actually get to why this happens, in case you're wondering. But this also brings up the fact that we're often aware of memory more when it actually fails us than when it succeeds, because it succeeds so often that we're actually usually unaware of it. And in fact, if it was failing most of the time, you would really know because we'd be unable to function in daily life. We have different kinds of memory. The great psychologist Endel Tulving, who actually would spend periods of time almost every year for a while here at UC Davis at the Center for Neuroscience, actually made a huge contribution by differentiating between two kinds of memory. One is called semantic memory. And so for those of you who hear about artificial intelligence, you might have tried out things like ChatGPT or Claude or Gemini. You probably hear about this all the time. Those kinds of AI systems resemble what Tulving called semantic memory. That is, they're basically representing information about the facts in the world. So I have kind of, for those of you who remember the TV show Dragnet, they talked about just the facts, ma'am. And so, for instance, if I show a picture of this guitar, I can tell you tons of facts about it. Way too many facts that anybody wants to hear, right? But when I show this guitar, it's not even the exact model of it, but I think of something else, and I think of it brings back something called episodic memory for me. And episodic memory is something that's associated with an experience called mental time travel. So I think, how many of you have ever heard a song and that song brought you back to a time and place? It brought you a feeling of pastness, right? So when you have that song that brings you back to a time and place, and I think almost all of you raised your hand, and it's just phenomenal how nearly universal this is. And I'll just ask another one. How many of you have ever had a taste of a food or a smell that brought you back to a time and place? Okay, so perfect. Almost all of you said this too. And this is such a near universal feeling. And what's amazing about it is when you hear that song or when you taste that food or you smell something or you go to a place, it doesn't just give you a sense of, yes, I have heard this song before. It brings you back to a moment in time. And that moment in time brings back all of this other information too. And that is what Endel talked about with mental time travel. And so this is what I study, is that form of memory that's associated with mental time travel called episodic memory. So for instance, when I see this guitar, I think of a time in my life when I had this guitar. And so this was when I was in college. That was my first electric guitar. This is me when I was in college. I think actually that was a particular house party that I was playing at. It used to be papered with stickers. This is now my Rosebud because I happened to sell it. For those of you who've seen Citizen Kane, I miss that guitar so badly. And I wish I hadn't sold it for like $100 to some random yuppie who was running down the street in Berkeley. But nonetheless, I see that guitar, I see a picture of that guitar and I want it back. It brings me that sense of mental time travel, right? So how does episodic memory work in the brain? I wish I could tell you all about all of our research. I'm just going to give you a little taste of it and a taste of where we're going in this research right now. So episodic memory, we know, depends on a brain area called the hippocampus. So the hippocampus is one of the first areas that's affected in Alzheimer's disease. It's affected in a number of other disorders as well. So for instance, when people have cardiac arrests and they go into comas, for instance, it's also highly affected in that. There's many other disorders as well, but certainly Alzheimer's is one of the most significant. Some of our research as well as others suggests that part of what makes the hippocampus special is that it indexes our experiences on a timeline. So here's recent work that we've done where if you basically scan people's brains, you can basically get brain images and use them like a QR code. And it's a little bit hard to explain, but if you get these images and you use them like a QR code, you can get these complex data sets and you can use methods kind of like actually what Rishi has done, and you can squash this down into a point in a three-dimensional plot. And you can make cool movies like this. And so what this shows is basically how activity in the hippocampus flows through time. And so I'll just show you this just to illustrate how activity in the hippocampus moves through time. And so the reason why I wanted to show this to you is just to illustrate that at any one given point in time, the hippocampus can create a little temporal index that basically allows you to take a snapshot of what's happening in the rest of the brain. And that index then allows you to be able to say, hey, at this moment in time, this is what was happening in the brain. And if you can get back to that index, now you can get back to all of these other points in time that was around that moment, right? And so when you hear that song, it can bring you back to that page in time, but now you have all those other nearby pages too that you can get to, right? And so this is the kind of work that we've done, and we've shown that when people, this is actually old data, long before this movie was taken, where we've shown that basically when people are able to accurately do that kind of mental time travel, the hippocampus seems to be involved in doing this. So what's really cool about this is that humans have episodic memory, and in fact, these AI systems don't. So you'll often hear people like Sam Altman from OpenAI talk about how, he'll even throw his son under the bus and say, or his, unborn child under the bus and say his unborn child will never be as smart as AI will be. And you often hear about super intelligence and so forth. And these systems do not have actual episodic memory. And in fact, I'm actually engaging in a lot of conversations with AI companies now about how they can actually incorporate human-like memory into these systems, right? But semantic and episodic memory together make us smart, and I've written about this. And what's really cool is every one of you has a unique episodic memory. You've got unique experiences. One of you had a random college roommate who was a philosopher who introduced you to Neil Peart's lyrics from Rush. And that gave you a unique episodic memory that no one else has. One of you had a random aunt who happened to be like in some kind of cult when she was, in her 30s or something like that. That gave you something that no one else has, right? And so all of those experiences allow you to come up with something in your imagination that no generative AI product could ever come up with. And as long as you each seek out your own diverse experiences that are not curated by some algorithm, you can come up with things that will keep you relevant in this day of AI. And so this is something I say over and over and over again to people, because I think right now we're seeing a little bit of a devaluation of what makes human intelligence so special. And I think the more we understand the brain, the more we realize how unique the brain is relative to these kinds of artificial forms of learning. So anyway, I'll move on off my soapbox because there's a lot more to go over, and I've definitely promised the organizers that I'll do a better job of staying on time than I have in the past. So I'm going to get into a little bit more of how we use memory in everyday life, because this is something that I'm getting more and more into, is trying to take memory out of these sort of past-oriented frameworks and really take it more into daily life. So I think many of you probably are familiar with the cartoon Peanuts, although I have noticed there's like an age difference in the audiences that I've talked to. But for many of you who've seen the Peanuts cartoon, you might be able to look at just this one frame of this cartoon and generate an entire movie about what's going to come up next. So maybe you can predict that this is going to happen. Maybe you could predict this. Maybe you could predict this. Maybe you could predict this. And then I can ask you, did you predict the ending? How many of you predicted the ending? Okay, great. So I'm guessing there is probably a generational difference there. But if you did predict the ending, that's because you have memory. And if you did not have memory, you probably couldn't predict the ending if you had never seen a Peanuts cartoon, right? And so that's the whole point. If you have memory, you can take these things that would normally be unpredictable and make the unpredictable routine, right? And so what we've been studying is how you can take memory and use it to make better predictions in life. And so what I've shown you is actually an example of something called event boundaries. So for instance, in that example, we had a case where you could basically create a little model in your head. From the first frame of that cartoon, you could create a little model in your head that you're not just seeing this cartoon. What you're really doing is you're seeing a little play in your head where Charlie Brown is looking at Lucy and he's about to kick the football. And that's the little play that you've created in your head. And you have a memory for an event that hasn't even happened yet, right? And so you don't even have to form an episodic memory for this whole thing because you've got this whole event in your head. But then as soon as she pulls the football away, now your understanding of what's happening is about to change. You realize Charlie Brown's about to get a concussion. He's going to need medical attention at this point, right? And so that point where everything switches and you have to change your mental model, that's what we call an event boundary. Now, it turns out these event boundaries have huge implications for memory. And in fact, it's changing our whole understanding of the neuroscience of memory, because so much of our experience is so predictable that in fact, we actually aren't forming memories for most of our experiences, it looks like. Now, I should say, we don't know this, but actually it's changing a lot of the ways I think about memory. And the reason is that, in fact, so much of our experience is so redundant that if we were to form memories for every one of these frames of experience, we would have far too much information, and that would produce so much competition in memory that we would actually have a lot of forgetting that would take place, and we would have a lot of capacity issues. It would just be a real mess. And so we think one of the ways our brain deals with this is to not use every point in the timeline that I showed you, but rather to take these most important moments in the timeline and use those as anchor points for episodic memory. So, how do we know this? Well, one reason we know this is that there's massive amounts of activation in the hippocampus and in the cortical networks that talk to the hippocampus at event boundaries. So here's a little map of some of the areas in the brain that activate at event boundaries. And this is work from one of my former postdocs, Alex Barnett, who is now a faculty member at McGill University in Canada. And it's not everywhere in the brain, but these are all areas that show high functional connectivity, meaning that they show correlated activity with the hippocampus. Now, what I'm showing you here is basically a bunch of people watched an animated film that Alex created. He's actually a multi-talented person, and so he created this film. And he just had a bunch of people push a button at a point where people said, yeah, one event has ended and another's about to begin. So people basically said, here's an event boundary. And these tall points represented a point where everybody agreed, yes, here's an event boundary. Now, a bunch of other people had their brains scanned while they watched Alex's movie. No pushing buttons, they're just watching a movie. And this red line represents the activity in those subjects. And what you can see is the activity in these areas in the temporal lobes lines up almost perfectly with the points that people think are event boundaries. This is activity in 546 people. In the same areas, basically these blue areas, for some reason Zach Ray, who's now a faculty member at Washington University, St. Louis, looked at this huge data set. He used blue instead of red for some reason, but basically found the same areas were activated in this gigantic data set. And so it's a very, very robust phenomenon. This is only 8 minutes worth of data he was looking at. It does not take a lot of data to actually find these effects. It's some of the biggest things I've ever seen in my career. Now, what's really interesting is and I'm not showing you these data in detail because it's kind of complicated to visualize, but basically when we've looked at activation during those points in time, like here, I'm actually in trouble finding here, if we look at activity during those event boundaries, like here's a point between two of the scenes in Alex's movie, what we find is the activity during that point in time predicts the ability of people to remember the entire event that came before it. So if people are remembering, let's say, the 40 seconds to which people remember the conversation of these policemen in the car, then people would show more activity at the event boundary. It's like as if people's brains are downloading an episodic memory during those event boundaries. What we found too is that activity in the hippocampus declines with age at event boundaries. So this is basically activity in the hippocampus timed right around an event boundary. And with fMRI, neural activity produces a response that takes about 6 seconds to kind of come up. So it's a little bit slow. But what you can see is for young subjects, it's pretty high. For older people, like around 60 to 80 years old, it's lower. It's still there, but it's lower. And here's what you can see. If each of these dots is one person and the amount of activation is on the y-axis, you could see that it glows down pretty steadily with age, right? But what's kind of cool is that Zach was able to separate this out and say, we can actually look at people's memory performance outside of the MRI scanner and just look at how good people are at retaining information in memory from stories and just say, is this a marker for memory independent of age? And in fact, it is. It's a remarkable predictor of memory for information outside of the memory scanner, even if we remove age from the equation. So one of the cool things we're doing now is we're looking at whether or not, we're looking at a huge study with collaborators in Germany to see if this can predict preclinical Alzheimer's disease. And in the opposite end of the spectrum, we're collaborating with researchers at the University of Chicago to see if we can find opposite effects in superagers. So these are people who actually are at the ages between at 80 years old who have memory performance that's comparable to people in their 50s. So stay tuned for that. Maybe another 5 years we'll have a super neurofest on that topic. So before we close up, I just want to talk about the role that event boundaries might play in preparing for the future, and Marty set me up beautifully for this. So I had some collaborators approach me about how we can actually use, how we can develop memory measures for people who aren't necessarily good at communicating in, let's say, English or something like that. And one of the things that we know is that the hippocampus is actually very sensitive to surprising events, like what I showed you with the Charlie Brown cartoon, right? And so this is work we've done with fMRI, showing hippocampal activity to surprising events. This is work where we've looked at electrical activity in the hippocampus, and these are basically oscillations, which are electrical sort of bursts of activity in the gamma band that are seen in the hippocampus for surprising experiences. That's what's shown up top. Versus expected experiences, there's not really much gamma activity going on there. And so what these researchers did was they said, let's try to basically use that to see if maybe we can come up with a way where we can measure memory for surprises using something that doesn't require people to say something. And we had actually done some research in our lab's past work and other people using eye movements as a measure of memory. And so just to illustrate this, I'm going to have you watch a little movie with me, and then I'll show you how this can work. So here's a little movie. This is a little bit more hip than Charlie Brown, but bear with me here.
Whoa, 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 whoa. We got a big issue, bro. Damn. You want to know what our issue is? You about to get jumped, homie.
All right.
You about to get jumped. You ever been jumped before? Well, you about to get jumped, bro. Ow! Ow!
So my collaborators actually came up with a whole bunch of these little short films that have these surprising things. Sometimes it would be like a seal and a bear would jump out of the water or so forth. And so what they did was they looked at people's eye movements when they would watch these videos for the first time, where people were watching literally with fresh eyes, versus the second time when people could use memory. And so what I'm going to show you is people's eye movements or fixations when people were watching when they could use memory, versus, which would be in green, versus when they're watching with fresh eyes, which is blue. And you can't quite see it so well when I show it in real time, but maybe what I can do here to make it a little clearer is what you can hopefully see is if you watch the green, can you see the green is going to the left there? So the green is basically showing that the person is looking at nothing for a while, right? Could you all see that? And I'll show it one more time just to illustrate that. So there's no reason that anyone in their right mind would look at that nothing patch unless you knew something was coming there, right? So basically, this has turned out to be a hugely sensitive measure for memory in their research, and they've replicated this a bunch of times. And one of the things that they're interested in is looking at how sleep affects memory. And so they're looking at they're looking at brain waves during sleep, and we know that those networks that I showed you in our fMRI studies communicate during sleep. There's this whole symphony of brain waves that you can see in the hippocampus and in the default network, which is that brain network that I showed you, that talk to each other during sleep. And basically they said, well, maybe what's going to happen is that there's going to be some kind of effective sleep on these indirect measures. Now, normally what can happen is if you sleep after learning, you get less forgetting than if you don't sleep. But in this case, people actually got better at predicting information after sleep than they were before sleep. It's one of the few studies I've ever seen where you actually get better at something after sleep than before sleep. So people are basically, their eyes go closer, which is what you see in green, to the actual prediction of where things should be than where you would be before sleep. So people are actually better after sleep, which is just phenomenal. So I guess if there's just one point I want you to take away from this is, I don't want you to see memory as necessarily some archive of the past. I really want you to see memory as this resource that we can dip into to understand the present, understand the future, and to really understand ourselves. And sorry about the little technical glitch, but anyway, if we have any time for questions, I'm happy to take your questions. Thank you.
Questions for Dr. Ranganath?
Hi, I was wondering whether and how, the event boundary effects relate to a lot of activities that we kind of do without really thinking about them somewhat subconsciously, and then we don't necessarily remember whether or not we did it.
Yeah, that's a great question. So how do event boundaries relate to activities that you do, but then you don't remember having done them? That's the question. Yeah, so this is a great one. So what can often happen is that for me, I'll be talking to somebody and then I get interrupted and then I'll find myself saying, what was I doing? I can't even remember anymore. And so what we think happens is that, remember I was showing you that smooth movement in the hippocampus. What we think happens is that in fact the hippocampus actually jumps in that space during these event boundaries. And so it's like you have to time travel really far back to get back to those moments to figure out what it is you were thinking about at those time periods after the event boundary. And that's also why you end up in the kitchen, because your sense of mental context changes so much. Your sense of where you are changes so much when you go into the kitchen that you have to actually, even though you've only traveled, a few feet, mentally you have to travel very far back in context space, in hippocampus space, to be able to figure out what you were thinking about too. So I do think it actually plays a role in that. Now, sometimes what can happen too is that in your daily activities, because we get so distracted with all of our devices, we often shift so many times back and forth that we actually just have, instead of one event, like I was showing you, we have 20 different fragments of events. And so what can happen is that all of those little bits and pieces don't really give us enough to work with to even come up with a good memory. And I think that's really kind of more of the modern problem that we have to deal with.
With the sleep, with the sleep, the memory getting better after the sleep, does it matter if the sleep is induced by medication or anything like that? Does that have an impact?
Great question. So from what we understand right now, Ambien, for instance, does not give you a natural sleep that actually improves memory. And that seems to be true of most medications, like, certainly alcohol will not improve your memory if you drink till you pass out. There appears to be, from what I understand, one recently FDA passed drug, I believe, that might induce a natural type sleep, and I don't think it's been checked out for memory effects yet, but for the most part, I would not expect drug-induced sleeps to actually improve memory.
Any idea how hypnosis affects the hippocampus, or maybe psychedelic drugs?
Yeah, so I'll speak to psychedelics first. So psychedelics massively improve plasticity. John Gray, actually one of our faculty, studies this very topic, and I feel like I can't even speak to it because he should be speaking here right now on this topic. But they're definitely plasticity bombs for the brain. And so that could be, increasing plasticity can be good and bad, because it's like, at some point, if you have lots of plasticity, you can basically wipe things out, right? And that's probably behind some of the effects of psychedelics on trauma, for instance. Hypnosis is a little bit different, and I don't know anything on the hypnosis on the hippocampus, but hypnosis it's basically a deep state of relaxation. And what we do know about hypnosis and memory is that basically it prompts people to become less critical of their memories because you're so relaxed. And that basically, the act of remembering something is in and of itself allows you to rewrite your memories. And so when you're hypnotized and you recall things, it allows you to kind of create something new. But if you're not being very critical, you can sometimes pull up information and imagine things that didn't really happen. And so that creates a susceptibility to generate false memories. And so I'm not a big fan of hypnosis for memory unless it's just kind of used for the purposes of just imagining things and having fun with it, or for the purposes of just kind of hypnosis for the sake of relaxation or self-improvement in some other way.
No, I'm not sure I actually how to phrase this as a question, but my grandson has very little episodic memory. So for example, he was at work and the boss said, go into the kitchen and get more plates. And he went into the kitchen, couldn't remember what he was supposed to get, and he had to do that 3 times before or 4 times before he remembered. And so we're all kind of trying to figure out what is his life like for him because they're just things he doesn't remember. Obviously, he's been able to learn. I mean, he learned to read. He doesn't read that well, but he does read. He learned to speak. So I'm just wondering if you have any like comments or insight into like how having very little episodic memory can affect your life, how you perceive things, how you remember things.
Yeah, so, I mean, there can be cases where, so when kids have real, like hippocampal damage, for instance, when they're very young, they can actually function very well, and it kind of masks the actual episodic memory problems. So sometimes it can be worth getting checked out because it can be kind of hard to spot sometimes. It'll manifest in terms of getting lost, or sometimes these kind of more subtle things, basically being slow to learn. There's cases of people who have been studied where it's like they can build knowledge about things that they learn in school, but when they talk about their life, it's like a story. They don't really remember events from their life at all. They don't kind of time and space, it just doesn't exist to them at all. And so those are the kinds of areas that they really struggle in, and especially like finding their way around the world, directions are a real problem for them. Separate from that, you find like people with attentional problems like ADHD can really cause a lot of memory problems though too, or other kinds of executive function deficits. And so if it's interfering with their ability to function, it's worth getting kind of a real comprehensive way of checking it out. But basically when kids have more executive function deficits, it's a different kind of thing. People have more issues with paying attention that generalizes beyond memory. It's more like kind of a general thing that would be like even in the moment in conversation, they're just off, right? So with memory deficits, it's more specific to things that involve not being able to remember, if that makes any sense.
I have two questions about dreams. First is that we always have dream every day, and we know that it's related to our memory. And I have a question: is the scene that we see in our dream related to the frequency that we see in our daily life, or like how surprised is it, or something like? Can we figure out a relationship between the scene that we see in our dream and our memory?
That's a great question, and I don't know. I'm thinking someone has studied this, and I wish I knew the answer to it. I can't give you an answer. I just don't know. I mean, I would imagine that frequency of seeing things in the real world would affect, at some level, the likelihood of seeing it in your dreams, but how much it would affect it is kind of, I just don't know. I wish I could give you a great answer to that. I just can't.
Yeah, because I think it's really interesting topic. I used to have a dream like I didn't see a person for a while, but just one night I just dream of him, and it's really feels like not really related to the day that happened to me, but it's really random and kind of sometimes you can also dream of something that you see in the day. Sometimes you dream of something that is far away from you.
Yeah, one of our theories of episodic memory, and we're not the only people who've thought of this, but is that, I was mentioning that episodic memories are kind of indexed on this timeline. And maybe one of the ideas that we have is that if you have these episodic memories on these timelines, what if you have some memory at this time and some memory at this time and some memory at this time? Maybe there's something across all of these times that if you could connect the dots, there's some really useful information there. And so one idea that we've had, and some other people have simulated this in computational models, is that if you could randomly activate those memories at different points in time, the brain can basically throw all these memories at the wall and see what sticks. And that might be why sometimes we can activate this information from things that you've seen long ago and then recombine it in these ways that just makes no sense at all. And in that way, dreams are kind of like imagination run wild, right?
Yeah, and
Thank you so much. We must move on. I've got one last question for you, Dr. Ranganath.
You briefly touched on trauma, and so I was wondering how your research may lend itself to people who don't want to remember. So things like post-traumatic stress disorder, where flooding of information can be impactful to someone's life.
Yeah, there's so much to say there. I wish I could. I mean, I want to give you 10 answers to this question, but I'll try to keep it as brief, as packaged as I can for Jennifer's sake. So, but basically, one thing we know is that not everybody who experiences trauma gets post-traumatic stress disorder. So there's kind of sometimes people think, well, if you experience trauma, you will get PTSD. But one thing that sometimes happens is that, basically PTSD is in some ways a natural brain mechanism for keeping people safe run amok, right? And so what we think happens is in part, the brain basically is using kind of context, kind of like what I was talking about with the timeline, using time and space to remind people, hey, something dangerous is about to happen. Now, in PTSD, that probably runs amok because especially when people undergo severe stress or chronic stress, it can be toxic to the hippocampus. And when you have damage to the hippocampus, now that timeline starts to become too blurry. And so anything can kind of activate the hippocampus, and these traumatic memories are especially sticky, and they can be reactivated very easily. And so what can happen is that you can activate these memories too easily, and every time you activate a traumatic memory in a new context, now it's like you get re-traumatized, right? And so these traumatic memories can become overgeneralized at different points. Adding to this is there's a hypothesis that Matt Walker, my friend, and I were texting about this, that sleep normally seems to play a role in kind of diffusing the sort of, so emotionally intense memories like trauma, there's a component of it that is this kind of visceral component, like your heart races, your eyes dilate, you get sweaty. And that part of it is separate from the memory of the context itself, and that's mediated somewhat by different brain systems. And part of what seems to happen during sleep is the separation and the toning down of that visceral part. But it doesn't seem to happen normally in PTSD. And so people with PTSD have these nightmares and it wakes them up and so forth. And so what happens is you have this overgeneralized fear response basically that activates these memories, and they're having these night terrors. And so you basically get these re-traumatizations over and over again. So what do you do about this? Well, part of it is that exposure therapy can help in terms of basically exposing people to these traumatic memories and habituating them to the fear response. In my experience, group therapy can play a part in terms of giving people a chance to get the social benefit of exposure to the traumas and kind of the social aspects of it. I'm giving you a very kind of broad answers to challenging questions. I feel that the psychedelic therapies might be promising here because they really do give a chance to kind of give people the therapy part where you're activating the memories in combination with this kind of plasticity bomb where you can really potentially revise the memories from a completely altered perspective. And I think that's potentially something that's very exciting. But I think the data just isn't there to say, yes, this is going to be the answer. So I think, it's a wait and see approach, but I think that could be really, I think some kind of approach like that, if pharmacology is going to be the answer, that's going to be probably the best direction to take.
Thank you so much, Dr. Ranganath.